So we were saying that a star like the sun starts in the main sequence, fuses hydrogen to helium, billions of years doing that, runs out of hydrogen, so the core gets smaller, and that causes it to heat up because it's squeezing, and then what happens is that you start fusing in a shell surrounding the core. So at first you're not fusing anything, and it swells up to be a subgiant. Then you start fusing in a shell, and then it swells up to be a red giant. And then the core is not really fusing anything at this point. The core is just mostly helium, and you've got a shell that's fusing hydrogen. Then you start fusing the helium. And again, you can get a helium flash. You get a really big star, it just gradually starts fusing helium instead of going to a helium flash. But for a star like the sun, it's going to go into a helium flash, start fusing the helium. So as it's doing that, you're fusing helium in the core. That's more like a star is supposed to be. So the core starts balancing out, and so you start heading back towards the main sequence. Now, what's happening, though, is you're fusing in the core much hotter, and you're fusing in a shell. So that's also going to be very hot. So what's going to happen is you're going to be heading towards the upper part of the HR diagram. So you start fusing, going off that way, and that puts you on the horizontal branch. But at some point, what's going to happen is you're going to run out of helium to fuse. Now, helium fusion turns out to be very less efficient than hydrogen fusing. So it's, you can sometimes make it back to the main sequence for a little bit, but sometimes some stars don't even make it back to the main sequence. They run out of helium before they even make it back to the main sequence, and so then the core shrinks again, just like before, back to a red giant. And as you go back to being a red giant, you're fusing in two shells around the core. You're fusing a shell that's fusing the hydrogen into helium, and that's surrounding a shell fusing helium into carbon. And then the core is just dead carbon. It's not fusing anything. You get a little bit of more fusion going on, but not by much. Okay, so you're running out of helium in there, swells up to be a red giant again, except now it's going to be a bigger red giant. We call this the asymptotic red giant. Asymptotic means parallel to, so the red giant branch is parallel to the other one. So the sun swells up to be a red giant again, and this time it's a bigger red giant. And so again, the additional fusion that can occur is that some of these carbons can grab an extra helium, okay, and makes an oxygen. So the core is actually going to be mostly carbon because you've used up most of the helium making the carbon. And then a few of those carbons will grab an extra helium, make an oxygen. So, so you end up with a carbon-oxygen core. Okay. So the core is mostly going to be carbon with some oxygen in there. And so here's a graphic that shows this sort of to scale, that you've got this core in the middle, okay, and the core is tiny compared to the size of the asymptotic giant. The asymptotic giant, or the second red giant, has a diameter here that's almost 2 AU. The radius is now almost an AU, not the diameter. And so the core is going to be mostly carbon with some oxygen in there, and there's no fusion happening there. It's a dead core. Surrounding that is a shell that helium is fusing into that carbon, and then surrounding that is a shell in which hydrogen is fusing into helium. So when the hydrogen fuses into helium, the helium is heavier, so it sinks into the lower shell where it's hot and compressed, and it fuses into carbon, sinks into here. If there's any kind of mixing that happens in here, that can bring a little bit of carbon in with that oxygen and fuse into, or helium in with the carbon and fuse a little bit into oxygen. But basically, there's not much fusing happening in the core. Okay, so this is the second red giant stage. Now, red giants, because there really still is the sun, it's just swollen up so ginormously that the outer edge of the red giant is a long ways from the center. Well, that means the gravity's a lot less. And so the gravity is determined by how far you are from the center. So when you swell up to be almost a radius of an AU, the gravity is about the same as it would normally be, 1 AU from the center of the sun, so about what it is at Earth. And so at that distance, it's really hard for the sun to hold on to its outer layers. And so the outer layers are gradually being pushed off into space, okay, an atom at a time. So this is like a solar wind on steroids. So this is a huge solar wind right here. In fact, we call it the red giant wind because we observe this with red giants. And so it's a low velocity wind because you're just gradually pushing things off. It's not this more high velocity wind that we have right now where solar activity is pushing things off. But this is a low velocity wind, but it's pretty persistent, and there's an enormous amount of stuff being blown off. For a red giant, somewhere between 10 and 80% of the mass can be blown away. The sun itself can easily lose almost half of its mass as this red giant wind. And so that's going to have a huge impact on the evolution of the sun. So this is a star, TT Cygni. Now remember, we said a lot of these red giants can be pulsating stars. They can be somewhat unstable. And surrounding it is an expanding cloud of gas given off as a red giant wind from that star. So, artist's impression of the sun from Pluto at this point. Because now the sun is enormously brighter and bigger. So even though it's cooler, it's enormously brighter, enormously bigger in the sky. And so even very, very far from the sun, it's starting to look big and bright. We'd already mentioned this before. These red giants can become unstable. That gives rise to all these pulsating variables that you see out there. And again, this is we've already mentioned this. We talked about variable stars, and I mentioned it again just recently. This is where you get these unstable pulsating stars.